Hello. It is a pleasure to be able to meet with my comrades in aluminium smelter world. In this occasion, I want to present the making of anode carbon in our company. Hope it can give inspiration to younger employees, especially for those who work in platinum in alum. Any ideas for the betterness of this presentation material is waited. Thank you. Carbon roll in aluminium smelter. 1. The Heroult process. Aluminum oxide Al2O3 is dissolved in molten cryolite 3Al6. It is decomposed electrolytically between carbon and aluminum electrodes at about 950 degrees C to aluminum and oxygen. The carbon anode is continuously consumed by reacting with the oxygen to give carbon dioxide CO2. To Al2O3 plus 3C equals for Al plus 3 CO2. 2. Reasons why carbon is used as electrode. Carbon are highly stable, requiring high temperature to react even with oxygen. Carbon has the highest melting and sublimation point of all elements. Thus, irrespective of its allotropic form, carbon remains solid at higher temperatures than the highest melting point metals such as tungsten or rhenium. Although thermodynamically prone to oxidation, carbon resists oxidation more effectively than elements such as iron and copper that are weaker reducing agents at room temperature. 3. Carbon known in various multiatomic structures with different molecular configurations called allotropes. The three relatively well-known allotropes of carbon are amorphous carbon, graphite, and diamond. Which one of these allotropes can be used as anode in aluminium reduction process? Amorphous. The amorphous form is essentially graphite but not held in a crystalline macrostructure. Graphite. At normal pressures, carbon takes the form of graphite, in which each atom is bonded trigonally. 2-3 others in a plane composed of fused hexagonal rings. The resulting network is two-dimensional, and the resulting flat sheets are stacked and loosely bonded through weak van der Waals forces. This gives graphite its softness and its cleaving properties. The sheets slip easily past one another. Because of the delocalization of one of the outer electrons of each atom to form a phi cloud, graphite conducts electricity, but only in the plane of each covalently bonded sheet. Diamond. That very high pressures carbon forms the more compact allotrope diamond. Here, each atom is bonded tetrahedrally to 4 others, thus making a three-dimensional network of puckered six-membered rings of atoms. That's why diamond to be an excellent electrical insulator. So, it is obviously that allotrope which is able to be used as anode material is graphite. This is microstructure of graphite made as anode. Due to the highest temperature might be possible happen in aluminium reduction pot. Still below 1100 degrees C, so it is no need to prepare denser graphite, just enough in between 1000 degrees C, 1400 degrees C. What criteria are needed from anode? Criteria for anodes. 1. High resistance to gasification in order to minimize dusting and excess of carbon consumption. 2. Sufficient mechanical strength for structural integrity and handling. 3. Low specific electrical resistance value for power consumption. 4. high elemental purity to avoid contaminating the reduced metal and excess anode consumption. 5. High thermal shock resistance to avoid cell disruptions. Where is our position in these tough demand? 1. GD80. Typical 1.55, 1.65. Inalum 1.64, 1.69. Status better. 2. BD80. Typical 1.50, 1.60. Inalum 1.59, 1.65. Status better. 3. AP. Typical 0.5, 2.0. Inalum 0.3, 0.5. Status better. 4. CS. Typical 40, 55. Inalum 28, 49. Status better. 5. FS. Typical 8.0, 14.0. Inalum 11.0, 15.0. Status better. 6. TC. Typical 3.0, 4.5. Inalum 3.2, 4.0. Status 7. RRO2. Typical 65, 90. Inalum 89, 93. Status better. 8. RRCO2. Typical 84, 95. Inalum 95, 97. Status better. Great. Why is it so difficult to achieve these figures? Unfortunately, no at all. No sacred matters here. Everything has been striped by R&D carbon. We just follow it in the correct direction and doing. Some proper adjustments to adapt plant condition and current. Raw material is being used. Here are the steps of anode manufacture. Let's talk about the first step, raw material. Cokes. Calcined cokes. Green coke is residual fraction of petroleum or crude oil which has a very weak amorphous structure and still has volatile matter in between 8 up to 12%. Cooked through delayed coking process then calcinated by giving heat treatment to make it as electrode quality coke or calcined coke. The coke's texture. Smelter grade cokes should have not too high real density and having tolerable impurities content. Too high real density will bring worse consequence during production and at last giving impact to quality. Pitch. For bonding grains, it is used binder from liquefied CDP. Coal tar pitch. Coal tar which is dewatered, heated up to approximately 350 degrees Celsius and finally flashed called distillation process will become coal tar pitch. So, what is coal tar pitch? Complex mixture between polycyclic aromatic and heterocyclic compounds with aliphatic and functional groups attached to the rings. Approximately 90% of coal tar pitch consist of 3 up to 7 ring aromatic compounds with molecular weights ranging between 170 up to 380. The remaining portion is made up of higher molecular weight carbonaceous materials that are not soluble. Why coal tar pitch is chosen as binder? 1. Strong adherence or bonding to the aggregate. 2. Satisfactory wetting characteristics. 3. High cooking value yielding a strong structure. 4. Low relative cost and ready availability in large quantities. 5. Low ash and sulfur content. 6. Smooth volatile emission across the anode bake temperature range. Coal tar pitch properties. 1. Softening point is used to describe the change in pitch between a solid to liquid form. 2. Cooking value is an indicator of the likely residual carbon retained in the form of pitch coke after baking. 3. Pitch density and CH ratio is an indication of the pitch aromaticity. Denser pitches have a higher aromaticity and thus produce denser baked anodes courtesy of a binder carbon yield. 4. Quinoline insoluble or QI describes the amount of particles insoluble in quinoline solvent alpha particles to be QI. There are 2 types of QI. 1. Primary, formed in the coke oven so it is good for anode quality. 2. Secondary and mesophase formed by additional heat treatment. Note, mesophase is harmful to anode quality. 5. Toluene insolubles or TI. Beta resin is TI reduced by QI. It will give beneficial to bond or forming ability of pitch with coke particles. 6. Viscosity is used to guide handling pitch liquid form and paste mixing and forming. 7. Distillation of lighter fractions. Lower temperature distillation of the lighter fractions is a measure of the pitch volatile content and lighter fractions that are released in the temperature range 270 degrees Celsius up to 360 degrees Celsius. 8. Ash content is an indicator of total impurities in pitch. The most important parameter from CDT is SP. The material comes from rotting plant. According to R&D, carbon, dust and grains less than 1 mm must not be recycled and treated as waste. How it could be? What is the reason for R&D carbon? The answer will come in a moment. Alas, sodium content increases higher in line with finer grains. So, that's why it is strictly not recommended. In order to get better anode, the bad character hine content in finer should be minimized in usage for recycling. That's all for the first step of anode manufacture. Next, I'm going to explain how to make paste. Let's talking about the second step, making good paste. Paste. Raw materials for paste are aggregate and binder. Let's talk these raw materials one by one, starting with aggregate. Aggregate is a mixing of cokes and butts. There are 2 preconditions should be fulfilled to get better aggregate. 1. Aggregate grains composition should be in the determined granulometry. According to R&D carbon, there are 4 possibilities of granulometry. 1. Intended to make denser green block with low porosity, which is at last after baking it is hoped we can get high RRA value. This kind of granulometry is our choice. 2. Intended to make denser green block with low porosity, which is at last after baking it is hoped we can get low AP value. Unfortunately, this kind of granulometry caused weaker physical strength. 3. Intended to make stronger anode after baking, but unfortunately this kind of granulometry has lower RRA and AP values. 4. It must be avoided, the worst granulometry option. Our choice granulometry no one in implementation organized such as the granulometry or distribution of grain size. To have denser anode, the granulometry should be arranged as the first course 16 mm down to 8 mm is 10%. The second course 8 mm down to 4 mm is 10%. Medium to mm down to 0.125 mm is 30%. Fine below 0.125 mm is 50%. Two. Aggregate impurities I.E. sodium, calcium, nickel and vanadium should be lower than determined values. Impurities should be attained in certain tolerable range. Catalytic impurities. Impurities which give bad impact to metal quality, silicium, iron, vanadium, nickel, titanium and lead. Impurities which give bad impact to anode consumption, vanadium, nickel, sodium, potassium and calcium. Impurities which give bad impact to energy and current efficiency, vanadium and phosphorus. Impurities which give bad impact to pollution, sulfur, hydrogen and lead. Now I show how to prepare cokes. Cokes disheartened from silos by ratio high sulfur, low sulfur equals 60 minutes and 40 seconds. Through damper DP, if coke silo level is still above 40%, no need bypass. In Silver SR1, grains separated into two size batch. Above 18 mm and in range 3, 18 mm. In Silver SR2, grains separated into 3 size batch. Range 3, 1 mm, range 1, 0.2 mm and below 0.2 mm. Grains with size over 18 mm is crushed by crusher to be finer than 5 mm, and then sent back to SR1. The surplus in 1 feed back into crusher to increase finer grain size product. To get fineness, grains with size below 0.2 mm milled into milk. The surplus in bin to feed back to tube mill to increase production of fineness. Fine comes from dust collecting system or bag filters. Pay attention on the texture comparison between cokes and butts. Let's magnify, and after doing it, can you catch any differences between them? Black color on coke is more dominant than butts. These black color spots are assumed as porosity. Butts have denser texture than cokes, or in other words, butts is weightier than cokes. Next images show which one is the best composition we should take. Composition 1. 1. All is butts. 2. At the same volume, it is weightier than composition 2 and 3. 3. Bonding among grains is not enough strong due to have only gluing and no anchoring. 4. Their reactivity and air permeability of the product anode will be worse. So, obviously that composition 1 is not recommended. Composition 2. 1. All is cokes. 2. At the same volume, it is lighter than composition 1 and 3. 3. It is going to consume more binder. 4. Many problems will occur after baking. So, obviously that composition 2 is not also recommended. Composition 3. 1. Mix between butts and cokes. 2. At the same volume, it has an ideal weight. 3. Optimal pitching can get. Obviously, this is the composition should be applied. Point to be aimed is how to get the best composition between butts, cokes in aggregate. Based on data showing in the chart, there are 3 conditions should be paid attention carefully. 1. Benefit got by using coarser butts. Grain size in between 0.5 to 16 mm is reducing porosity up to 70%. 2. Meanwhile, coarser cokes grain decreases 50% porosity. 3. Significant impact coming from finer grain either cokes or butts. Let's say it's able to reduce porosity above 90%. In this range area, it's better to utilize butts, in order to increase weight, and at last will be increase the density. In this range area, it's better to utilize butts, in order to increase weight, and at last will be increase the density. In this range area, consider to use same portion of cokes and butts. Maximize cokes in this area. There are no significant white difference. This can also avoid dirty butts dust entering the aggregate. So, let's skin the density of butts and cokes on each areas. From the granulometry composition we have chosen, we can get data. Now, we make a simulation to look for the best composition to get higher density. Let's do trial and error method to fill the table. But ratio equals 34% and VBD aggregate equals 0.9323 g/cc. CDP must be in liquid form in order to act as binder, but before talking further, please acknowledge information regarding CDP. In depth with CDP. 1. By using many different kind of solvent, like alcohol, toluene and quinoline. Substances on pitch can be grouped as alpha-resin, molecular weight is under 100. Toluene soluble, molecular weight 100-1000. Quinoline soluble, molecular weight 1000-3000. Two. The sticky characteristic of pitch contributed mainly by beta resin, which is a difference of quinoline insoluble, toluene insoluble. Beta resin equals K, T. Note, more beta resin greater than better sticky characteristic of binder. So, to represent more beta resin greater than increase amount of K. This is commonly done by add lighter fractions into distillation. This will increase the risk of metaphase appearance. Three. Sometimes, too high key content will give bad impact to pump performance. It's strainer clogged by a thin layer. So, be wise in choosing CDP. Mesophase, theoretical review. When pitch is made, aromatic systems are growing up in thermolyses and leads to a sufficiency. High concentration of large aromatic systems with molecular weights approximate to 600 AMU. Mesophase occurs if some critical parameters e.g. viscosity, heating rate and others are met. The mesophase is strongly anisotropic and takes a spherical form in order to minimize its surface energy. Further about mesophase. At further heating or increasing residence time, more and more mesophase is formed from the isotropic pitch. The size of the mesophase spheres increases and they start to coalesce into bigger and bigger anisotropic areas. The transition from a flowing or plastic pitch to a rigid semi coke green coke occurs in a narrow temperature interval, around 500 degrees C. Still a significant amount of hydrogen is present, but most will be gone when the temperature reaches 800 degrees C. So, obviously that too much mesophase with high diameter will leave behind voids after baking process. It's clearly harming anode quality, and this is so bad. This data inform the amount of mesophase and heat adjustment to keep pitch viscosity in order to keep as good binder agents. This data inform the additional percentage of pitch in order to cover the existence of mesophase in binder. What kind of pitching should be achieved in order to get good anode? Let's know kind of level pitch given into paste. Case 1. Underpitching. Underpitching symptoms: 1. Dry paste. 2. Cracks on GB. 3. Underdocking, lack of volatiles. 4. Poor mechanical properties. 5. Airburn problem in pot. Case 2. Overpitching. Watch out! Overpitching at last in bond grains due to cohesion greater than adhesion. Overpitching symptoms: 1. Wet paste. 2. Glowing paste. 3. Extreme shrinkage. 4. Stump hole deformation/slumping. 5. Crack during baking, excessive devolatilization. 6. Sticking of packing material. 7. High air permeability, compressive strength and Young's modulus. So, what does the optimal pitching look like? Case 3. Optimal pitching. Optimal pitching: 1. Still left void. 2. No separate bonding among grains. Now we have came to how to achieve optimal pitching by setting correct binder ratio. To do this, firstly, we have to know the limit of overpitching by comparing slumping on BB. Watch out! Look at figures 15% and next higher level. In this range, GB80 is not in line with BB80 anymore. What does it mean? Yes, of course, GB80 can be made higher by increasing binder level, but result after baking. Delimitate it. So, this phenomenon becoming the first sign of overpitching. Secondly, check the sticking either amount or pattern on BB. Remember, there are two kind of sticky things on BB. Just after discharging from baking furnace: 1. Isolation coaks. 2. Another blocks. Whatever the sticking kind, this pointing to the second indicator of overpitching. Note, we apply constraint value 2% of sticking on BB from the total BB discharged. Listing the figures into databank for the next product. Please, keeping this databank update. Are there any different methods? There are two methods to detect binder sufficiency. It should be done by operator during inspection. 1. Physical inspection on GB condition, looking for symptoms of overpitching, like glowing on GB crust, length shrinkage greater than 3 mm. 2. Observation on paste condition just before forming, like flaccidity, tough or fragile. Now, we have come into the making of paste. Beware! Kept the temperature of this paste product always plus 10 degrees C than temperature needed in forming machine. What should be paid attention in kneading or mixing operation? What should be paid attention in kneading or mixing operation? 1. Softening point is p-value of the current CDP. Important. Inalum using ball ring methods, so it has to be adjusted by -5 degrees C. For operation purpose, correlation between softening point and mixing temperature is described by equation y equals 1.48x plus 5.6, where y equals mixing temperature, x equals softening point. For example, if SB equals 113 degrees C, so mixing temperature equals 170 to 8 degrees C. By implementing Black's principle, we have formula for thermal balance. Let's say we have data. SP of CDP from India equals 113 degrees C. Binder ratio equals 14.5%. Heating up temperature for CDP equals 210 degrees C. Heating up temperature for aggregate equals 160 degrees C. How big additional temperature should be given? Answer. First, we are looking for mixing temperature. Put in SP value into the first formula, we have 172.84 degrees C. Put in data into the second formula, we have equation 0.145 asterisk 210, T equals 0.855 asterisk T, 160. So, we will get T equals 167.25 degrees C greater than we need 5.59 degrees C more. Let's try to implement this formula. Please follow the movement of star pointer on the chart. This situation takes place if no additional heat, so it is strictly prohibited. In order to achieve appropriate mixing temperature, an additional heat from meter should be given. Two. The second important factor during kneading process is specific mixing energy. Mixing energy. The best practice in Inalum to get homogeneous paste is by implementing mixing energy inside a tight space. From 8.9 up to 9.1 kilowatts flash-ton paste. Below this range, paste looks dry. Above this range, paste looks wet. 3. Mixing time. Look, either shorten or prolong the mixing time, in fact it is no use. Important stuff related to mixing time. Too short makes underpitching. Too long may destroy granulometry of the grains. What we want is sufficient time in order to give binder and fineness centering macroporosity of grains to create anchor bonding among binder matrix outside and inside grains. Note, it is applied mixing time around 5 minutes. Please, look at description comes in a moment. Inside meter, forces coerce binder matrix to enter coax grains. After cooling, this binder matrix will build stronger bonding compared to gluing only. Let's talk about the two-road step, paste forming. Steps of shaking machine operation. 1. Charging paste into the ready mold. Note: paste is not something liquid, so it cannot fulfill the whole space inside the mold automatically. We have to arrange its spreading evenly during filling time. In order to avoid sticking of paste in the mold wall, precaution actions should be done before forming, like A. Heating up or keeping temperature stable. B. Spraying special oil and water in the wall regularly. C. Removing residue in the mold from the previous forming. In order to get one side having better density, we can increase thickness on this side. Paste profile intentionally created, not flat. Or you can't try for the opposite side. 2. Put cover weight down and then lock up. What should be paid attention regarding cover weight? A. To weight the cover weight leads to grain destruction, and thus to an insufficient strength of the anode. B. To light the cover weight results in a poor density and an excessive gas permeability. Note: specific forming pressure versus anode cross-section. Equation: Y equals -459.1 x superscript 3 plus 1655 x superscript 2, 1931 x plus 800.7. Y equals specific forming pressure bar. X equals anode cross-section m superscript 2. 3. Evacuating unnecessary gas or PA emission by vacuum. Usually for better result, make it below 120 mpr. It's time for vibrating now. For vibrocompaction operation tips. Paste temperature put into the mold should be in between 155 degrees C to 165 degrees C. Avoid paste temperature variance. Federal into mold vary more than +/2 degrees C. In order to get better result, it is strongly suggested to make input paste temperature close to the highest constraint equals 165 degrees C. This effort is going to decrease viscosity, so it is easier for grains moving to find its optimum place in mold during vibration. DBNSIDROL. This is control program on the vibrocompacting machine. Control principle by this program can be explained. 1. The first priority, the machine look for GB80 value or GB height. If one of these target is found, then stop. 2. Secondly, if during set maximum vibrocompaction running, these two targets don't get, then stop. Note: the machine is completed by weighing scale and height sensor, so it is able to adjust the amount of paste fed if the height of previous block down below. Beware! Just after forming, block exhibit a low mechanical stability due to the softness of binder pitch. In order not to damage the block, handling with care is a must. So, to release block from mold, pusher should be run gently. Finish. Prepare to form next block. Cooling after forming. After forming, GB temperature is still high. It exhibits low mechanical stability. Due to this reason, it needs to be cooled. This is very important phase on the making of anodes. Mishandling will cause damage on GB. 1. Cool to intensify, may cause surface fissures are generated due to shrinkage of GB crust. 2. Insufficient cooling, may cause damage on GB during subsequent handling, storage and processing. Here, in a moment, show to you the steps of cooling phase. Be careful, this period needs a lot of care or just leave it more safe. This is a sample when weak crust is in dangerous period but handled. Just before I end this presentation, let me explain how to keep the quality. First of all, you should know well the basic knowledge. In GB production, do you know that the most important thing from paste plant to make sure the GB product always in the good quality are just to control impurities content coming from raw material and get ideal GB80? As simple as that, isn't it? I have developed the formula to predict anode quality, based on GB data. Calculation result with this formula compared by actual results show just a little difference plus minus 1%. RRO2 equals negative 216.218 Ni, 972.153 V, 105.415 No plus 190.783 Ca plus 1.642 S, 2.336 GB80 plus 106.183, where RRO2 equals air reactivity residue percent, Ni equals nickel content percent, V equals vanadium content percent, Na equals sodium content percent, Ca equals calcium content percent, S equals sulfur content percent. RRCO2 equals negative 238.741 Ca, 24.253 Na, 46.022 V plus 1.105 S plus 96.524, where RRCO2 equals co-to-reactivity residue percent, Ca equals calcium content percent, Na equals sodium content percent, V equals vanadium content percent, S equals sulfur content percent. So, by controlling each impurities involved and arrange ideal GB80, best quality anodes are in our hand. Regarding achievement and ideal GB80, like or dislike, it depends on the goodness of equipment and skill in blending raw material. Experience is the key. But here, I just share some tricks. There are two conditions: down under and over the top. Basically, both of them are caused by granulometry. Countermeasure for down under: 1. Increase the usage of coarser butts material if enabled. 2. In case you don't have coarser butts, consider increased butts ratio. 3. In case you have only sufficient butts stock, consider to decrease production capacity. Countermeasure for over-the-top. 1. Decrease the usage of coarser butts material if enabled. 2. In case you don't have finer butts, consider to crush it. 3. In case you have too much butt stock, consider to increase production capacity. In this position, the cause is still same with down under case. Just use the same trick to overcome this problem. In this position, the cause is in forming machine or kneader. Just follow the tricks already explained to overcome this problem.